Next we will discuss about momentum integral method. When we learn any technique, there should be a purpose, and it is important that we first discuss about the purpose of this, that why we are going to learn this before understanding that what actually the method is. See, as I told you a few times before, in engineering it is important to evaluate certain parameters of engineering interest. One such important parameter is the wall shear stress for interaction between the fluid and the solid, because if you want to pump a fluid over the solid, you have to overcome the wall shear stress. So that is a cost that you have to pay to maintain the flow. Therefore it is important that we know how to calculate the wall shear stress. Now to calculate the wall shear stress, of course you can calculate the wall shear stress by using this method, but we have seen that this method is little bit more involved, in a sense that it requires the solution of a third order ordinary differential equation, which is not having any analytical solution. So we are trying to look into a little bit more simplistic approach, yet not so inaccurate approach of solving the same problem of calculating the wall shear stress. So how to do that? The name itself suggests what we are going to do. We are going to integrate the momentum equation. The momentum equation is nothing but the boundary layer equation here. I mean, one of the boundary layer equations is the momentum equation, the other equation of course is the continuity equation. So we will integrate both the continuity equation and the momentum equation across the boundary layer, and that is why it is called as momentum integral method. So let us write. So we consider laminar boundary layer over a flat plate. So we will write the boundary layer equations These are our boundary layer equations we derived in the previous lecture. So what is the first step is we will integrate with respect to y from 0 to delta. Okay. So that is the first step. Then what we do? Well, we simplify the second term. For that we integrate by parts. So this is the first function, this is the second function. The reason is obvious, because the second function is having a higher order derivative. Integral of the second function will be the what we evaluate during the integration by parts. So one order derivative will come down. So this will be first function into integral of the second minus integral of derivative of first into integral of the second. Okay. Now we can write that this del v del y is nothing but minus of del u del x. Why? This is because of continuity. Del u del x plus del v del y equal to 0. Okay. So this term is, it becomes plus u del u del x, then there is another term plus u del u del x. So basically you come up with integral 0 to delta 2 u del u del x plus what is this? What is v at y equal to delta? Whatever, let us give it a name v infinity. We have clearly seen that it may be small, but it is not 0. So v infinity into u infinity minus v at 0 into u at 0. Okay. So v at 0 is 0 because of no penetration, u at 0 equal to 0 because of no slip. Very interestingly, the result of this method does not change if there is a slip at the wall. The reason is, even if there is a slip at the wall, that is u at the wall is non-zero, still v at the wall is 0 because of no penetration. So the product will be 0. Then this equal to integration of this is what is del u del y at y equal to delta? What is the value of del u del y at y equal to delta? 0, because at y equal to delta u becomes uniform, after that u does not change. So the derivative of u with respect to y will be 0. So it will become minus nu del u del y at y equal to 0. See, one of our objectives was what? To calculate the wall shear stress, and this is nothing but tau wall by rho, because tau wall is mu del u del y at y equal to 0. Now there is still an unknown in this equation, which is v infinity. So we will try to obtain v infinity by using the continuity equation. we will integrate this equation with respect to y. So, what is this? This is V at delta minus V at 0, minus V at 0 is 0. So, V at delta is V infinity. So, V infinity is equal to minus integral of del u del x So, with this V infinity we can substitute in this equation. So, in this equation we will substitute the V infinity which we have got from the continuity equation. So, that will become integral of 0 to delta 2 u del x dy plus in place of V infinity we will write minus del u del x dy . So, this can be written as del x of u square, right. So, if you now consider these two terms together, it will be integral of 0 to delta del x of u square minus u infinity dy. Okay. Now, the next question, and this is a very important question, can we bring this derivative out of the integral? Can we bring this derivative out of this integral? That means, can we write this as say del x of integral 0 to delta u square minus u infinity dy, yes or no? See, first of all we have to understand that by our wish or whimsies we cannot take any derivative inside and outside the integral as per our like. There is a rule which is called as Leibniz Rule, which talks about differentiation under integral sign. Let us look into that rule and try to apply that rule here. So let us say that fxy is a function of x and y. So when this is integrated with respect to y, there is no more dependence on y, there is dependence on x only, that is why it has become d dx. Okay. So now this derivative, it can be taken inside the integral, but with these correction terms. This is the Leibniz rule. See, in engineering or physics or mathematics, there are so many beautiful things that we often overlook, and it is one of such very beautiful examples where the mathematics in some way talks about very interesting physics. We have discussed about Reynolds transport theorem. The rate of change with respect to system is equal to rate of change within the control volume plus outflow minus inflow. So this is like rate of change with respect to system, this is like rate of change within control volume, this is like outflow minus inflow. So it is like a physical situation being represented by a mathematical equation which may be derived independent of that physical situation. Anyway, that is not our objective, I just made a passing remark concerning this one. Now in this example, what is f? What is f in this example? U square minus u infinity. What is a? 0, and b is delta, which is a function of x. So let us look into the correction terms. F x b db dx. What is f x comma b? At b, or b means delta, at delta this becomes u infinity square minus u infinity square. So this is 0, and dA dx, f x a dA dx anyway is 0 because a is 0, so dA dx is 0. So you can see that the correction term is 0, right. So sometimes actually ignorance is a blessing. So if you do not know the Leibniz rule, you straight away say I will take the derivative outside the integral, you save a lot of time. And this is how many times students are tutored for competitive exams. I mean you are trained to use certain formula for solving certain problem. The formula may be correct, but the way of arriving at the formula may not be correct. So there are many books which immediately after this step will write the derivative outside the integral. So it will create an impression in your mind as if that is the rule that has to be there always. But this is the rule. Fortunately the correction term is 0 in this case. Okay. So you will get see now what should be the strategy of calculating the wall shear stress? You will be able to know the wall shear stress if you know how u varies with y, because then you do this integration and then differentiate this, right. So the question is we do not know how u varies with y, but what kind of variation is expected? See, this is the integral that we are going to calculate, u into u minus u infinity, right, dy of course that I am writing. So, if you write this as u infinity square, you take outside the integral, then it is u by u infinity into 1 minus okay. So, u by u infinity is a function of y by delta. What kind of function? Say something like this. Let us say you do not know this. So, instead of this you make an approximation, say some approximation, say this, some approximation, say it may be linear, it may even be sinusoidal, it may be quadratic, it may be cubic, some kind of function you approximate. So, clearly this is erroneous, but see the very interesting thing, it is not of importance to us what is the error in the function, it is important for us what is the error in the integration. Now, integration wise, see if you have integral of say f dy, say this is f as a function of y. So, integral f dy is the area under the curve, right. Now, instead of this, if you approximate it by this curve, you make an error in area which is this, right. The first observation is that the relative error in this area is much less significant as compared to the error in the function. So, integration in some way smoothens out the error. The second observation is that here the function is multiplied by its complement 1 minus the function. So, if there is some positive error in calculating integral of f dy, that is nullified by the negative error in calculating 1 minus f dy. So, the net effect is that even if you make some very poor approximation in u by u infinity as a function of y by delta, the net effect of that in calculating this integral is not that severe. So, with that understanding you can actually use any approximate velocity profile, but with the satisfaction of the proper boundary conditions you have to do that, so that you are able to calculate this parameter. So, the use of the momentum, this is known as von Karman's momentum integral equation. Of course, when Karman derived the momentum integral equation, he derived for a general case, not for flow over a flat plate. So, there the dp dx term was also there. This is the special case of the momentum integral equation where the dp dx is equal to 0 for flow over a flat plate. Now, let us take an example. let us consider a polynomial, say up to cubic polynomial. You can also take higher order or lower order polynomials. Mod number of constants, mod will be the constraints that you can put as boundary conditions. So now what are the boundary conditions that need to be satisfied? Most essential boundary conditions. Say you had taken u by u infinity is equal to a0 plus a1 y by delta. Had you taken that, there would be two constants a0 and a1, so you could impose two boundary conditions. What are the two boundary conditions you must impose? First is at y equal to 0, u equal to 0, no slip boundary condition, and the second is at y is equal to delta, u equal to u infinity. These are the basic boundary conditions. So let us write that. Here you have 4 constants, right? Because you have 4 constants, that means you have to put 2 additional constraints. What are the additional constraints that you can put here? If you want to give a priority, that is, let us say you have up to the quadratic term, then what is the next priority? These are the 2 high priority boundary conditions. These 2 must be satisfied. The third one, see what happens at the edge of the boundary layer. At the edge of the boundary layer, the velocity does not change any further. So that means at y equal to delta, del u del y equal to 0. And then what is the fourth boundary condition? Because these 3 boundary conditions more or less come directly from physical intuition, but the fourth one is not something which will come directly from physical intuition, but you have to give a little bit more thought into that. So let us write the boundary layer equation somewhere. U del u del x plus v del u del y is equal to nu del 2 u del y 2. So now with this hint you tell what could be the boundary condition. If you apply this equation at y equal to 0, at y equal to 0, this is equal to 0, this is equal to 0, therefore this must be equal to 0, right. So at y equal to 0, so now it becomes a well defined problem with 4 constants need to be evaluated from 4 constraints. I will not go through the algebra, I will leave it on you as a homework. So you show that homework u by u infinity is equal to 3 by 2 y by delta minus half y by delta whole cube. This is if we take this example. If you take other velocity profiles, of course there will be different coefficients. So with this velocity profile, our next objective will be to calculate delta as a function of x, the wall shear stress as a function of x, and I will illustrate that with this velocity profile, with other velocity profiles like linear velocity profile, quadratic velocity profile, sinusoidal velocity profile. These you do as a homework. The answers are given in any textbook on fluid mechanics, and you can check your answers with those books. So we will continue with this and use that in the momentum integral equation. So u infinity square dx of integral 0 to delta u by u infinity into 1 minus there is a minus here, right? So I have, what I have done is I have swapped this term I have made the first term and this term second term and divided by u infinity. So because I have swapped the term, this minus has become plus. So now you write u by u infinity is 3 by 2 y by delta minus half y by delta whole cube. Okay, that velocity profile. So y by delta, let us call y by delta equal to eta. So dy is equal to eta d delta. Sorry. With respect to y, delta d eta. Right. Because when you are differentiating y at a given x, this is the variable that is changing, eta is changing. So this becomes u infinity square d dx of integral, if you change from delta to eta, this is 0 and this is eta equal to 1. U by u infinity is 3 by 2 eta minus half eta cube, 1 minus u by u infinity 1 minus 3 by 2 eta plus half eta cube, dy is delta d eta. So that delta we can bring here because delta does not depend on eta. What is del u del y at y equal to 0? At y equal to 0, del u del y is 3 by 2, 3 u infinity by 2 delta. From the velocity profile. So I will not waste any time in evaluating this integral. this may be very tedious, but there is no special trick which you can play. You have to just simply multiply and integrate these polynomials. So, let us say that this is equal to some number a. Okay. So, u infinity square delta d delta dx is equal to 3 u infinity nu by 2a. So, 1 u infinity will, let us write u infinity here in the denominator. So, delta square by 2 is equal to 3 nu x by 2 a u infinity plus some constant C1. Okay. Now, as x tends to 0, delta tends to 0. As I told you earlier, at x equal to 0, delta is not defined. So, it is x tends to 0 plus actually. That will mean C1 equal to 0. So, delta square is equal to 3 nu x by a u infinity. That means delta by x all right. This if you evaluate, this will come to be 4.64. These are very classical results in fluid mechanics. Okay. So, see what is the difference in the result from the similarity solution. Similarity solution is the correct solution. There it was 5. Now, instead of 5 it is 4.64. It may appear to be quite inaccurate, but our ultimate objective is not to calculate delta, but to calculate the wall shear stress. So, let us see that how does it fare in calculating the wall shear stress. So, what is tau wall? Tau wall is this, right? So, that is remember u by u infinity is 3 by 2 y by delta minus half y by delta whole cube. So, tau wall is 3 mu u infinity by 2 delta. normally the wall shear stress is expressed in a non-dimensional form by using this non-dimensional parameter Cf, which is called as skin friction coefficient. This is tau wall by half rho u infinity square. And delta is, what is delta? Delta is square root of 3 nu x by a u infinity. So, this becomes if there is any algebraic mistake, please let me know. But I am trying to do it generically, that because this integration will be different for different choices of velocity profiles. So, given that integration, how you proceed with calculation of the remaining thing, so that you know the procedure and you can apply it to any velocity profile that eventually you have to consider. So, this will typically be 0.646. And the drag force how do you calculate the drag force on the plate? This is the ultimate engineering importance. How do you calculate the drag force on the plate? So, let us draw the plate like this. So, at a distance x, you take a strip of width dx. What is the force on this? Let us say that the width of the plate is b and the length of the plate is L. So, what is the elemental drag force on this? First of all, why do you have to choose an element? You have to choose an element because the wall shear stress continuously varies with x. So, you have to take a small element over which the wall shear stress is like a constant. So, what is the wall shear stress here? Let us say tau wall. So, tau wall into b into dx. Okay. So what is the total drag force? Now what is the drag coefficient? Coefficient of drag. CD. This is the non-dimensional drag force. So this is Fd by half rho u infinity square into B into L. So now you can substitute the values. You can write tau wall as a function of x. Tau wall is what? Tau wall is 3 mu u infinity by 2 delta. And this delta is a function of x. Delta is square root of 3 nu x by a u infinity. Okay. So it is finally a polynomial function of x that you integrate with respect to x and do it. If you do this, then you will come that this is equal to a coefficient into Reynolds number to the power minus half. That coefficient is typically double of that is 0.646. If you do this problem by, or if you work out this problem by the similarity solution, this will be like typically 1.33, 1.332 like that. So see, the error is really very small. Instead of 1.29, it is 1.3 or 1.33, and this is the main dependence, Reynolds number to the power minus half. So it shows one very interesting thing, that although there is error in the choice of the velocity profile, but that error is somehow smoothed out when you calculate the wall shear stress non-dimensionally or the drag force non-dimensionally in terms of the drag coefficient. Then that error is not that much. So you can use these velocity profiles, whatever approximate velocity profiles, to first calculate delta as a function of x. See, delta as a function of x is the main thing, because once you know delta as a function of x, the drag wall shear stress or the drag force all are functions of delta. So if you know delta as a function of x, you can evaluate the local friction coefficient or the overall drag coefficient by integrating that delta as a function of x. So knowing delta as a function of x is important, and we can use the momentum integral method to evaluate that delta as a function of x in a somewhat accurate manner. So to summarize what we have learned so far, we have learned the hydrodynamic boundary layer. What is a hydrodynamic boundary layer? What is boundary layer theory? What are the boundary layer equations? And two techniques for addressing the boundary layer equations. One is the similarity solution technique, another is the momentum integral method. Now we have to keep in mind that at the end our objective is not just to study fluid mechanics in the course of heat transfer. We want to utilize this understanding of fluid mechanics to solve problems in heat transfer. And for example, when we studied flow over a flat plate, we want to next study heat transfer over a heated flat plate or heat transfer over a cooled flat plate. How to address that? we have to utilize or we have to derive equations which, just like Navier-Stokes equations for fluid mechanics, will be useful for solving the temperature distribution in heat transfer, and that is nothing but the energy equation. So, in our next class we will derive the energy equation for convection heat transfer. Thank you.